ठीक है, so अच्छा, we're gonna start with the first question, which is ये वो transition, it's on transition metals, ठीक है. So let's start with this one. So name the type of reaction. I'm just going to go over this. This is ligand exchange, ठीक है. But remember, this is ligand exchange. State the colors. Remember the colors of your complexes. With what is the color with water?
Pale blue.
ठीक है, this one is blue. Or with Cl, it's going to be
Yellow. Yellow green.
greenish yellow. Yeah, green yellow, greenish yellow. And also remember the colors with cobalt. Cobalt with water is pink, and cobalt with Cl is blue. I just state the shape. What is the shape of this ion, of this complex?
Tetrahedral.
Okay, this one is tetrahedral. It's a tetrahedral, 4 bonds, 4 ligands. So this one is tetrahedral. You have to write the K stability expression for which equilibrium? For this equilibrium, this one, right? So it's just products over reactants. You don't write water in the expression because it's aqueous. Okay, so you don't. So it's going to be CuCl4. 2 minus concentration. I said, make sure when you do this, put the charge inside the bracket, because the square brackets, they represent concentration. So Cu with 6 water molecules, and you have a charge of +2. It's concentration, and you've got Cl -1. And that is 4. So yoga. Then you have what is meant by the term bidentate ligand. So it's a ligand that is capable of forming
Two dative bonds.
two dative bonds in a metal complex. Okay, so it has 2 lone pairs and is capable of forming 2 dative bonds in a metal complex. What do these K stability value tell us about the relative position of equilibrium? When you have a higher value of K stability, what does that mean? Equilibrium side, where is it shifted? Forward or backwards?
Forward.
Forward, right? So this is higher. So relative position, this is shifted to the right, or you can say, relatively speaking, this is shifted more to the right compared to the first one.
Sir, wait. जब ज़्यादा higher K stability means that the ion is more stable.
That means ligand exchange will happen. But the K stability, you should know the definition as well. That K stability is that in an aqueous solution, when you try to do ligand exchange, it's the equilibrium constant for a ligand exchange reaction in an aqueous solution. So you've got an aqueous solution. Starting point is always going to be a water complex, a complex with water molecules. Okay, the starting point would be an aqueous solution. Okay, the definition of K stability is it's the equilibrium constant Kc for a ligand exchange reaction in an aqueous solution. So if you have a higher value, that means you get more products, which means that this particular complex is more stable. Okay, that means this is more stable. If you have a lower value, that means this is more stable compared to the other one. Okay, clear?
Yes, sir.
Okay, so that one is more stable. So coming back to this, well, the one marker, you're just going to quote whatever the position is. Next one is nickel forms the complex ion nickel En2+, in which it is surrounded octahedrally by 6 nitrogen atoms. Name the type of stereoisomerism displayed by this thing, and draw a 3-dimensional diagram to show the 2 stereoisomers of this thing. Did he give us the structure of En? En is this thing. It's this diamine. Just 1 second. I say it's a diamine. It's a bidentate ligand. So remember, stereoisomerism happens. You have to remember this exact example, okay, and you should know how to draw this. Okay, stereoisomerism happens in bidentate complexes. Okay, these are your X, Y, and Z axes. And he's saying draw the 3-dimensional, so you have to draw the whole thing. So it's NH2 and NH2 on this side, and there's going to be CH2 and another CH2. ठीक है, और ये they would be connected together. Then another NH2, and in the middle there's going to be two CH2s, and over here as well.
सर देखिए अब it doesn't matter कि आप like किस
हाँ
के साथ कौन सा वाला
हाँ नहीं,
random हो सकता है.
हाँ, it doesn't matter, ठीक है. But I could have attached it over here, ठीक है, over here and over here. The other one is going to be a mirrored version of that, ठीक है, that would be the other one. So you have to learn to draw the other version as well. So it has to be exactly, everything has to be exactly mirrored, ठीक है. So make sure you know how to draw the mirrored version of this. And remember, this is the only time when you have stereoisomers. There are actually two times. One is that you have three bidentate ligands. So there's going to be a mirrored version of this same one. There would be two different three-dimensional shapes of a molecule, right? Or there's another scenario where two of them are a bidentate ligand, and on the third side, there might be a monodentate ligand. So you don't necessarily need, okay, on the third side, you don't necessarily need a bidentate ligand. You could have Cl-1 ligands as well. Even in that case, it's going to show stereochemistry. It's going to show optical isomerism. Okay, in this case, we had to draw the other one. So now the next part is ethane 1,2-diamine is used as a useful reagent in organic chemistry. Explain how amino groups in this allow the molecule to act as a Bronsted-Lowry base. So you can write an equation. First thing is, so you have to explain this as well, okay? So I mean, you have to explain this. So you've got NH2s, and the NH2 has a lone pair, so it's going to accept an H+1. So that's an equation, and it will form NH3+1. And also remember that it's usually going to form just one. It's only going to accept one H+1. I mean, most of the time, the most likely scenario is that it will only accept one H+1. There's another lone pair as well, but that would be very difficult for it to accept an H+1, because once you accept an H+1, it becomes a positive ion. So it becomes harder for the other one to accept an H+1, because the positive ion will repel the other positive ion. So further dative bonding will not be possible. The other thing that you're going to write about this is that you have to explain this. So lone pair on N forms a dative bond with H+1, or attracts H+1, and they end up forming a dative bond. That's it. So that's 2 mark. The equation is over here, actually. Write an equation for this. So let me just quickly open the MS for this. Okay, how are the marks distributed? Why are they giving 2 marks for that?
Sir, नीचे वाले में तो reaction with an excess of HCl लिखा है.
हाँ, but लेकिन उसको you can write an ionic equation, like, I mean, you can make it HCl, like add the Cl-1. Okay, that's it. I mean, the Cl-1 is not really doing anything. Okay. But let me just quickly. But the 2 marks would be distributed. One would be for the lone pair, one would be for the dative bonding that's happening. So it's lone pair and it accepts a proton. So if we write that it datively bonds with H+1, that is kind of the same thing. They were talking about a base. Okay, how is it behaving as a base? So I think it was important to write that it accepts a proton, or you should have written that. TK in this explanation. The equation is over here. Now the next part is, under certain conditions, 1,2-diamine reacts with the carboxylic acid. Draw the structure of the polymer. So polymers, this is polyamides that is going to form. You have to draw the structure of the polymer showing 2 repeat units. So for 2 repeat units, okay, there's going to be NH2 on one side. So you would have to draw 4. So you would have to draw 4 of them. There's going to be a carboxylic acid next. Okay, that's the carboxylic acid on both sides. Then again, there's going to be NH2. And NH2 on the other side as well. So I'm just going to draw three of them. The H and the OH in the middle would form water molecule. There's going to be a condensation reaction, and so the H at the end will also go away, and they will join up, and they will form amide linkages. You should have drawn a fourth one as well because they were asking for 2 repeat units. Remember, this entire thing is 1 repeat unit. This thing gets repeated after that, so you should have drawn 4 of them. ठीक है वो तो check भी कर लेते हैं. That's 4. They've drawn a skeletal formula, but that's kind of the same thing. They didn't actually ask for the skeletal formula. They just asked for the structure. So both of them would be acceptable. Name the type of reaction. That's condensation. And remember, condensation polymers are all biodegradable. What's the reason why condensation polymers are biodegradable?
Polar bonds होते हैं तो
ठीक है, so
get easily hydrolyzed.
The carbon has a positive charge, the oxygen has a negative, the lone pair over here that's negative, the hydrogen is positive, so they're going to attract water molecules and they're going to react with water molecules. So the linkages will eventually break. So which polymers are non-biodegradable?
Things like PVC and so on.
Addition polymers. Addition polymers are non-biodegradable because they only have a carbon chain. Like if you have polyethylene, it's just carbon atoms it's a chain of carbon atoms, and carbon atoms are non-polar. So they would be non-biodegradable because they won't attract anything, and the carbon bonds are kind of very stable as well.
Sir, polyesters भी biodegradable होंगे ना?
हाँ, क्योंकि वो भी polar है. If in a polyester.
Excuse me, sir.
Yes.
सर उन्होंने नेम करने के लिए नहीं बोला, लाइक हम किसी स्पेसिफिक पॉलीमर का एग्जांपल नहीं देंगे इधर?
अच्छा हाँ, नेम करना है. नेम polyethylene. ठीक है. अच्छा, how many addition polymers do you know of? That's polyethylene is one. ठीक है, that's your normal everyday plastics, polyethylene bags. You've got PVC. ठीक है, you've got PTFE. ठीक है, these are the common ones. लेकिन चेक कर लेते हैं, what do they mean by named? हाँ ठीक है, they wanted a name. So it's a polyalkene, polyethylene, PVC, etc. Even PTFE would work. PTFE is more non-biodegradable because the CF bond is like really, really strong. So next one is predict what would be observed when anhydrous copper to carbonate is heated. That's decomposition. So what would be observed? What would happen?
Sir, fizzing type due to carbon dioxide gas.
It won't be fizzing because fizzing happens in a solution. You're heating a solid and that's turning into another solid. You wouldn't notice the gas escaping. I mean, I doubt.
So you find solid remains.
So what would happen? What's the color of copper oxide? What's the color of copper carbonate?
White.
The colored compounds. Copper oxide is black in color.
Yeah.
And copper carbonate is green.
Yeah, that's true.
Okay, this is colors of compound. I mean, copper carbonate. I mean, the colors of copper carbonate are not really in your course, but you should know it's O levels. It's you've studied this in O levels. Copper oxide is black in color. Okay, I'll just check to confirm. Okay, which part is this? This is. I said again, they didn't. The colors would be fine because the colors were not part of your course. I mean, especially colors for copper carbonate. So that's why they're avoiding that. But that answer would be fine. Like if you just write that copper carbonate, which is green, turns to black copper oxide. So they went for the most generic observation, which is solid remains. Okay. But again, this is also correct. Okay, is that clear?
Yes, sir.
So describe and explain how the thermal stability of the group 2 carbonates varies down the group, they become more stable, right? And what's the reason explanation for this?
The size of the red eye, the size of the ion. Yeah.
Okay, so the ionic radius increases,
Mm.
which decreases charge density. So it decreases charge
Yeah,
density
charge density decreases.
and polarizing power decreases,
Yeah.
or polarizing power of the cation decreases.
And
So the carbonate ion becomes more stable.
yeah.
So the simple explanation for this is that if you have a small ion like Mg and it's got a +2 charge, Mg has such a strong positive charge that it will polarize the carbonate ion, which it's attracting, right? And what
Mhm.
it will do is it will attract the electrons from the carbonate ion so strongly that the Mg will eventually pull the oxygen out of the carbonate ion, and the other atoms would leave as carbon dioxide. So the carbonate ion would split up. The oxygen electrons will get attracted to Mg. The Mg will strongly bond with it, and the carbon dioxide would break away. So the carbonate ion becomes more unstable if you have a small ion. Bigger ions won't do that. They won't attract the carbonate ion that strongly. So this one, Cn2 minus, right? So Cn2 minus. Now we know that carbon makes 4 bonds, right? So carbon is going
Yeah.
to make a double bond on this side,
And another double.
and it's going to make a double bond on this side. So carbon has its 8 electrons. Nitrogen has a total of 5 electrons. So right now, 2 of them are being shared. So there are 3 electrons that are left. The other nitrogen, 2 electrons are being shared. So 3 electrons are left. So the nitrogen outer shell is not complete. It needs 1 more electron. So that 1 extra electron is going to be the square symbol. So now nitrogen also has 8 electrons, but 2 electrons came from outside. So that will give it a 2 minus charge. Okay, clear?
Yes, sir.
And it readily decomposes with water to form an insoluble white solid and ammonia. So CaCN2, when it comes into contact with water, it's going to form a white solid, which is, what is that white solid? And ammonia gas only.
Calcium carbonate.
That's a, can it be calcium carbonate?
Calcium oxide.
So lots. What is left? I mean, it has to include a carbon because where did the carbon go? So again, there are only 2 products that are formed, right?
So calcium.
So I think the only option left is calcium carbonate, right?
Mm.
Because it's going to have calcium, it's also going to have carbon in it as well.
Carbon.
So the only white solid that's possible is calcium carbonate. And you can then balance this equation. It's going to be 2 NH3s, and that's 6H, so 3 H2Os. And I think that's balanced. The oxygens are also balanced. Okay, because we had to fit in the carbon as well, so we went for calcium carbonate. This one very quickly, magnesium with hydrochloric acid entropy change, is it positive or negative?
Positive.
Okay, and why is it positive?
Hydrogen gas pencil.
Okay, so hydrogen gas is getting.
Magnesium chloride plus hydrogen gas is formed. Yeah.
So what you're going to write is gas moles increase, right? Or gas is produced, or gas moles. I mean, that would be sufficient. Potassium chloride dissolving in water. So what is that? Positive or negative?
Positive.
Okay, positive. And why is it positive? Because what's
Since
it?
it is dissolved in water, so the molecules are moving more.
Okay, so you're going to write that it dissociates. The ions dissociate in aqueous state. and more particles are produced. I mean, you had just one particle, they were all together, right? But in water, the particles have all dissociated. So ions dissociate, uska wording, and the number of particles in solution increase. I mean, that could be a further, it's just one line. So has free moving aquasines. That's what they wrote. The solution has free moving aquasines. It's a steam condensing to water, so that's obviously
Decrease.
a decrease. So it's negative. And the number of gas moles they decrease. Okay, that's why. So you've got this reaction. So very quickly, we have to figure out delta G now. To figure out delta G.
सर एक सेकंड ऊपर जाएगा. सही सर.
That's the next part. You've got delta G for the reaction, or it's you have to calculate delta G. Delta G, to calculate delta G, you would need delta H minus T delta S. Now you know delta H, you know the T as well. What you don't know is so you know this thing. What you don't know is delta S. So you have to calculate delta S first. So how do you calculate delta S? Delta S is calculated using the formula, the entropy of the products minus the entropy of the reactant. So somebody should do this pretty quickly. What are your products? These are your two products. So it's this and this. So 26.9 plus 214.
Minus 61.
And you're going to minus the MgCO3, which is 65.7. So what do you get?
175.2.
So we're getting 175.2. And be very careful. Delta G is in kilojoules and entropy change over here is in joules. So make sure the unit is the same. I mean, this thing that you've calculated, that's in joules. So delta H is 117. And
1000 से divide कर देंगे.
And delta S is 175.2, but that's in joules. So it's going to be divided by
1000.
1000. Okay, that. And remember, delta G is in kilojoules. Delta H is in kilojoules. Delta S is in joules. So what do you get for this?
52.2.
64.
52.
This one. So 64.8. You're getting 64.8. See, that's 64.8. So next, I explain with reference to delta G why this reaction becomes more feasible. So for a feasible reaction, what should the delta G value be?
It should be negative.
It should be negative. It should be exothermic. The overall system must have. It should be releasing energy. So delta G is the gives free energy. So it should be negative. So if you want to make it negative, that means delta H minus T delta S must come out to be negative. Now delta H is positive. That's endothermic. And delta S is, what is delta S? Delta S is also positive. But it has a negative sign, so it actually becomes, I mean, the second term actually becomes negative because of the negative sign over here. So if I want to make delta G overall negative, I would have to make my negative term bigger in size. It has to be larger in size. And it can only be larger if the temperature is greater. So if you increase temperature, what you're going to write, the reaction becomes more feasible. If you increase temperature, you're going to write that minus T delta S becomes more negative if you have a higher value of T. And if it becomes more negative, that means the overall delta G would become more negative. So reaction becomes more spontaneous or more feasible. Okay, so to make it spontaneous, it has to be, T has to have a bigger value. You clear? Is this clear?
Yes, sir.
So now the next one is you've got calculate the minimum temperature at which this reaction becomes spontaneous. So it's the same question. Delta G has to be less than 0. It has to be negative, right? For a spontaneous reaction. So if you want the reaction to be spontaneous, What is delta G? Delta G is equal to delta H minus T delta S. So that means if I say that delta G has to be less than 0, that means delta H minus delta T delta S must also be less than 0, because delta G is equal to this thing, right? So we need to solve this inequality. Delta H is given, that's in kilojoules, minus, I am trying to figure out the temperature. I don't know what the temperature is, and the entropy change is in joules. So I'm going to divide that by 1000, and I have to make this less than 0. So I'm going to take 130 to the other side. So this side would become minus 130, right? So now I have minus T into this thing. I'm going to take this number to the other side as well. That's going to become 1000 divided by 316, right? And always remember that when you're dealing with inequalities, if you change the sign, this sign is negative and this sign is also negative. I need to get rid of the negative sign on both sides. So if you switch the sign, or you multiply it by -1 on both sides, the inequality direction will change. It's going to switch. Always remember this, that -5, -3, -5 is smaller. But if you change the signs, the direction of the inequality changes. 5 is bigger than 3. So just make sure you don't make that mistake. You have to switch the sign as well. So basically at the end of the day, T is greater than 130 times 1000 divided by 316. So what do you get?
111.
111. So 111 Kelvins, right? 411.
411. 411.
411. So that is your answer for this one. Again, a question. I've just memorized this one. This is a typical question. Why do the solubility of sulfates decrease down the group? So down the group, you're going to write that delta H, since it's decreasing, that means delta H solution becomes more endothermic. So they've already the reason it's 2 marks because they've already told you that it decreases, right? So it becomes more endothermic. Why does it become more endothermic? Down the group, the ionic radius increases. And what does that do? Because of that, when you want to dissolve something, you would have to do 2 things. There's positive ion, negative ions, negative, positive. You would have to break the lattice. That's the first thing. So the positive ions and the negative ions, they all get scattered. And then you want to hydrate them, that they should attract water molecules and bond with them. So down the group, both lattice energy and delta H hydration, they decrease. They should decrease. But one of them, enthalpy of solution is basically what? It's the sum of the 2 things. You're breaking the lattice, that's the negative of lattice energy. That part is actually endothermic. And then you're forming bonds with water molecules. That is enthalpy change of hydration. Since you're forming bonds, that part is exothermic. So if the overall thing is becoming endothermic, that means the endothermic term is bigger compared to the exothermic term. So if both are decreasing, but lattice energy
hydration decreases less.
So, or lattice energy decreases less. This is going to be relatively bigger and this is going to be smaller.
Yes.
So this decreases more down the group and this decreases less. Compared to hydration. Just make sure this question will come in your exam. It comes in every exam about solubility of group 2 sulfates or hydroxides. For hydroxides, it's the opposite. They become more soluble, so the enthalpy of solution becomes more exothermic. And if it becomes more exothermic, that means down the group it is decreasing. Bigger ions, they form weaker bonds, but in that case, since it's becoming exothermic, so this is relatively bigger compared to this one. So this
Sir,
decreases.
can I see the marking scheme for this one, please? Alright, sir.
It becomes less negative down the group or decreased.
Okay, sir.
And delta is decreases more compared to the other one.
Alright, sir.
So next one. Wait a second. So we have another question on cobalt transition metal. I'll just go through this. It's it's a D block element that forms stable ions with incomplete D subshells. So state the formula of each of the. So what happens? What is the formula of when you add OH ions to this?
CO, OH2, and H2O4.
Well, even those water molecules, because once it becomes neutral, it forms a precipitate. Even the water molecules eventually leave. Okay. I mean, you can.
Sir, ये किस type का reaction होता है?
This is precipitation. Remember this. This is not ligand exchange. Because what happens is initially this is ligand exchange, that the water molecules, they get replaced by OH ions, right? Lekin eventually this entire thing, it becomes neutral. So when the whole thing becomes neutral, even the water molecules that were part of the complex, they would eventually leave as well. And it would.
This same thing happens जब हम NH3 aqueous डालते हैं.
हाँ, शुरू में. When you add a small amount of NH3, the same thing happens. Okay. Cl ions add करोगे, you'll get CuCl4 minus. And when you add excess NH3, so this thing will not happen. It's not with excess NH3. When you add a small amount of NH3, this thing will happen. So in this case, you're free to choose whatever amount of NH3 you want to keep in the formula.
Okay.
It could be 3 NH3s and 3 water molecules, or it could be 6 NH3s, or it could be 5 NH3s and 1 water molecule. So this one is C. Colors, what's the first one? What's the color for the first one?
Pink.
I just sorry, cobalt. I was thinking it's copper.
Mm.
Now remember, cobalt. The first one is not pink. You can remember the first one is not pink. This is blue. किसका?
उन्होंने दूसरा फॉर्मूला दिया हुआ है. उन्होंने दूसरा फॉर्मूला दिया है. H2O वाला दिया हुआ है.
ठीक है. मैं ऊपर ही देख रहा था. अच्छा, this one is definitely pink. अच्छा, what is with Cl? What is the color with Cl?
Blue.
ठीक है, with Cl it's blue.
Cobalt,
and what is the color with the cobalt?
I can give you yellow.
With NH3, what is the color with NH3?
It can result in yellow or.
It's not yellow. It's
brown.
It's brown. Okay, I'll just go through this very quickly. Where's transition metals? Sorry, this is AS. Just 1 second.
Sir, OH के साथ क्या होता है? Copper.
Cobalt?
Yes, cobalt.
I think green होता है. Just 1 second. This one. So these are the main ligand exchange reactions, right? That you have to remember. Copper with water, you add NH3, copper becomes surrounded by NH3, you add Cl, you add OH ions, it eventually forms a precipitate of copper hydroxide. These are cobalt complexes. TK with OH ions, it forms a green precipitate. With NH3, it forms a brown solution. With water, it's pink. With Cl, it's blue solution. Okay? And these are exactly the same complexes that you'd get with copper as well.
So with excess of ammonia, will we say green or will we say brown?
The excess ammonia?
Yes, sir.
Okay.
Brown, okay.
Small amount of ammonia डालोगे तो the ammonia, when you add a small amount of ammonia, this is what happens. Okay, if you add a few drops of ammonia, the ammonia
Yeah.
acts as a base initially, so it starts
Same,
reacting with
sir.
water, produces OH ions. So you get OH ions. Or when you add excess NH3, the OH ions get replaced by NH3, so you eventually get NH3 surrounding it.
All right, sir.
So remember, syllabus, it's just copper and cobalt. And you have to remember these 8 colors. I mean, 4 for cobalt and 4 for copper. Okay, these 4. As anyways, moving to the next question, we've got define the term standard electrode potential. So it is the potential difference between.
Sir, एक मिनट, ये जो हमने A किया है, cobalt hydroxide, ये green नहीं होना चाहिए.
नहीं, hydroxide नहीं, cobalt with water है. Cobalt with water.
Cobalt with water is pink.
Pink.
अच्छा, सही.
ठीक है, when you add OH ion, so just like copper में you get a blue precipitate, over here you get a green precipitate. When you add excess of ammonia, you get a brown solution. Copper के अंदर you get a deep blue solution. ठीक है. COCl4 is blue solution. CuCl4 is a yellow solution, greenish yellow solution.
I mean, this cobalt with water complex is being added to OH ions. So how do we know कि सारे OH H2Os replace हो रहे कि सिर्फ
With
दो
NH3?
replace हो रहे
नहीं,
कि
with
तीन
NH3?
replace हो रहे तो
नहीं,
आपने
with
सारे replace कर दिए.
हाँ, इसके अंदर I've told you previously as well that that the number of NH3s are variable. You can add 6 NH3s, or you can add 4 NH3s and 2 water molecules. I mean, as long as there are 6 of them, it could be any combinations of NH3 and water molecules. So that's variable. All 6 could be NH3. So there is no rule for that. All of them would be acceptable. But with OH ions, remember, it's always going to be 2. Because after 2 OH ions are added, the complex becomes neutral and it no longer attracts OH ions. Okay? So no further OH ions will be attracted to this precipitate. Okay?
अच्छा, alright, ठीक.
बस ये
तो
NH3
cobalt copper के लिए दोनों OH मतलब सेम ही है अगर +2 है तो मतलब 2 ही OH ions आएंगे.
हाँ, but ये जो कुछ the same, everything is exactly the same for cobalt. Everything is exactly the same except the colors are different. That's it. Okay? Even these equations are exactly the same. Okay? They're going to ask you to write equations about ligand exchange, so they would be exactly the same. Like what would happen if you add concentrated HCl to CO2 plus aqueous? They're going to ask you to explain that. So you can explain that for copper. You can also do the same thing for cobalt as well, except that the colors would be different. That's it. The equation would still be the same, exactly same. Okay, repeat for cobalt, just different colors. That's it. Okay, is this clear?
So could you repeat how would we explain एक बार?
नहीं कि no, we get a question. He's going to ask you that you've added copper 2 plus aqueous. I mean, you have a copper solution, aqueous, and they're adding concentrated HCl to it. So okay, explain what's going to happen. So you're going to write, first thing, you're going to write an equation. Okay, copper in aqueous is basically copper with 6 water molecules. If you're adding concentrated HCl, so you're adding 4 Cl ions, and those Cl ions are going to knock out the water molecules, and the 6 water molecules are going to get displaced. Okay, that's a ligand exchange.
Sir, तो यहाँ पे why not 2 molecules of chloride ताकि balance हो जाए? Copper 2 plus or
he's adding concentrated HCl. That's why.
अच्छा हमारे कोर्स में मतलब I mean is there
उसमें they're not going to ask you about variation of that. I mean there are obviously variations in this, but that's not in your course. Okay. You just have to remember that if you add concentrated HCl, then 4 Cl ions are going to replace the 6 water molecules. You can
and the same reaction works for cobalt to
हाँ
cobalt
मतलब
as well, right?
just replace copper with cobalt. The colors are
ठीक है,
different.
yeah.
It's going to be ये वाला क्या होगा, copper with water, it's going to be pink, and cobalt with Cl is going to be क्या था
Blue.
Cl sorry, it's blue, yes.
Blue.
So it's just going to be exactly the same. Then they're going to ask you about, I mean, they're basically going to ask you about this. Okay, they're going to ask you to write explanations for these 4 reactions. That's it. So you just have to give equations like if you have copper with 6 water molecules, you add NH3, this happens. Okay, so you can write an equation easily. Okay, that's you add concentrated HCl, this happens. You add OHNs, this happens. Except for NH3, you just have to go into a bit more detail that if they are adding NH3 slowly, drop by drop. So first thing would be a pale blue precipitate forming because NH3 will form OH and those OH would form the copper hydroxide precipitate. And then when you add NH3 in excess, then the NH3 ligands will start replacing the other ligands. And you'll form a copper with NH3 complex. So, but most of these are going to be very straightforward, very simple, very basic. Okay. So moving on, define the term standard electrode potential. So we did that. Okay, what did we do? It's the electrode potential between a standard electrode and a standard hydrogen electrode, measured under standard conditions.
So standard half cell and standard hydrogen electrode एक ही चीज होता है?
Standard half cell? A half cell is an electrode.
Yes, sir.
A half cell is an electrode. I mean, to make a complete cell, you need 2 electrodes, right? So half cell would be an electrode basically. So मैं देख लेता हूँ if it's
half cell related definition में
it's going to be the same thing. It's going to be the same thing. It's an electrode or a half cell, same thing. An electrode is a half cell. Okay, but is this clear?
Yeah, I think they're just being noted in the marking scheme.
And when it's compared to or connected to a standard hydrogen electrode or a hydrogen half cell. So next is next one is we've got as I write an equation for this. So you would need a value. Does anyone have a data booklet? 1 second. What is the potential for this one? So cobalt, I think it was, what was it? It was cobalt 2 plus and cobalt. It's this one. That's minus
0.28.
Achha, minus 0.28. Achha, the other one is Fe3 plus Fe2 plus. That's 0.77. This one. Okay, that's 0.77. So higher potential gains electrons. So this is going to gain electron. The other one is going to lose electron. Okay. So that is what's going to happen. So they're asking for the equation. So this is minus 0.28. And this other one is 0.77. So I'll just make the equation over here, Fe3 plus. So this one is going to gain electrons. The other one, cobalt 2 plus 2 electrons in equilibrium with cobalt. So that is going to lose electrons. The electrons have to be balanced first. So this would be multiplied by 2. And then you add up the reactants. So the reactants are 2 Fe3 plus. In the second equation or first equation where the reactant is your cobalt. And in the products, you're going to have cobalt 2 plus. And in the second one, the product is 2 Fe2 plus. And you have to calculate the E naught cell. So it's a reduction potential, E naught minus, always, I mean, it's basically higher potential minus lower potential. But this, I mean, this would be it's going to be very useful if you remember it this way.
The lower potential को reverse में लिखेंगे ना?
हाँ, मतलब वो minus आप difference निकालना तो automatically minus हो जाता है. असल में reverse पे कोई नहीं लिखता. वो जो reverse वाली, वो reverse में वैसे ही हो जाता है वो, क्योंकि when you अच्छा एक सेकंड, क्योंकि होता ही है कि what happens is that when you calculate a difference, it's higher minus lower, so the other side would automatically become minus, so it's going to be 0.77 minus 0.28 and whatever that is 0.99 क्या होगा, it's 20, yeah, 20, that's 0.97, 1.05. Okay, that's going to be 1.05. The next is the electrochemical cell in D was set up again, but this time the concentration of cobalt ions was 0.0. This is the Nernst equation. So use the data booklet and the Nernst equation to calculate the value of E. E is the non-standard potential for the cobalt 2 plus half cell in this experiment. So we already know the E naught. The E naught is already given, that's minus 0.28. So I'm going to find the non-standard potential. So the non-standard potential would be E. The E naught I know is minus 0.28 plus 0.059. What does Z stand for?
Sir, E naught 1.05 नहीं था?
नहीं, E naught,
Electrons.
Z is the number of
Electrons?
electrons. ठीक है, 2 electrons. अच्छा, remember, the Nernst equation is not for the full cell, ठीक है? मतलब ये तो E naught cell is for the full cell. It's for the electrode only. You remember this thing? You can't,
Alright sir, सही है, समझ आ गई.
you can't apply the Nernst equation to the whole thing. It will get applied indirectly to the whole thing. I mean, you'll find the non-standard potential of this thing. You might find the non-standard potential of this thing, and then when you do the difference thing, so you'll find the cell potential of the whole thing.
Not so.
हाँ, लेकिन you can't,
Actually, not 1.05 नहीं है.
ये भी मैं बता रहा हूँ ना कि पूरे सेल के ऊपर Nernst equation is not applied. ठीक है, Nernst equation is for one specific electrode.
Yeah, that's true.
ठीक है, you'll find the non-standard potential of this. Then you'll be asked to find maybe the non-standard potential of the other one. Then you can find the E naught cell of the whole cell. ठीक है. So over here, he's just asking for the cobalt 2 plus and cobalt half cell. So 0.059 divided by 2, and it's going to be log of the
Reduction.
concentration of cobalt ions, which is given as 0.05.
सर 0.05 को
जब
लॉग लेके
हमसे-
उसको मल्टीप्लाई कर दे सबके साथ.
हाँ,
ओके.
सर जब हमें नर्न्स्ट इक्वेशन यूज करनी होती है ऑन टू डिफरेंट आयंस, तो तब हम लोग ई नॉट सेल किसका लेते हैं?
you can't use it for two different. Na? I'm explaining that. You
सर
can't.
जब वो लिखा होता है कि फॉर एग्जांपल Fe2 प्लस ओवर दिस डिफरेंट आयन, राइट, तो फिर हम लोग ये ई नॉट सेल ये वाली नहीं ले सकते, उन दोनों में
नहीं,
से
इसमें
इंडिपेंडेंटली कोई एक लेनी
let's
होती है.
say we have a hypothetical question that they've changed the concentration of cobalt ions and Fe2 plus and Fe3 plus, right? And they're asking you to calculate the new E naught cell. So what I'm saying is you can't apply the Nernst equation on the whole equation.
No.
You would have to. हाँ,
इसका नर्स इक्वेशन के अंदर जो लॉग के आगे ऑक्सीडाइज्ड ओवर रिडक्शन की कंसंट्रेशन नहीं लिखते थे.
हाँ ये वाला, दैट्स व्हाट आई वाज saying.
हाँ वही लिखते थे ना, तो I'll explain.
Reduced हमारे पास solid है तो.
हाँ,
that
इसलिए
won't
इसलिए
count it.
that is taken as one. One of them is a solid. So oxides over reduce, if you do that, this is aqueous, right? So this is the oxidized species. The left-hand side is the oxidized species. The right-hand side is the reduced species. So it's going to be oxidized species over reduced species. So it's going to be cobalt 2 plus ion aqueous concentration divided by the cobalt solid, and that's going to be taken as one. So इसलिए ना, that's why they didn't write that over here.
सही है सर.
तो लेकिन in this case में टेंशन लेनी भी नहीं थी, क्योंकि they already gave the equation for you. You just had to plug in the values, ठीक है. But लेकिन वो वाला, if you have two different ions, remember this. I'm just going to go over that once more. If you have two different ions, remember you can't apply the Nernst equation on this entire thing. ठीक है, that is not going to work. You would have to find the individual electrode potentials using the Nernst equation, and then you can use those values and find the overall E naught cell, which would be obviously different. ठीक है, is that clear?
Yes sir.
Achha, Agla, suggest, what do you get? Suggest how this change will affect the overall cell potential compared to E naught cell. in D3 is the standard potential. So I said they're decreasing the cobalt ion concentration, right? So where would the equilibrium shift if you decrease cobalt ion concentration? It's going to shift in the backward direction.
Backward.
So is it going to become more negative or more positive?
More positive.
No, it's
More
going to be
positive.
more negative.
More negative.
Okay,
Sir, why the cations ज़्यादा form नहीं हो रहे?
electrons ज़्यादा form हो रहे हैं. Electrode, the electrode has electrons on it. So more electrons are
ठीक है
going
sir.
to, okay. So, but simple, remember this. Cations are getting formed, right? But they're in the solution. They're not on the electrode. Okay. So if you talk about the solution is becoming more positive because it's got more cobalt ions, right? Mic throw. As a solution is becoming, as it's becoming more positive, but we're not talking about the solution. We're not measuring the potential of the solution, we're measuring the potential of the electrode. So the electrons are accumulating on the electrode. So always remember, if the whole equation shifts to the left side, the potential will become more negative. So it's going to become more negative compared to minus 0.28. Vice versa, if it shifts to the right side, then it's going to become more positive. So in this case, it's going to become more negative, which means less positive. Sorry. Over here, he's talking about the E0 cell now. Okay, what is the so over here he's talking about this thing, not about the individual potentials, right? So Perez, explain what happens to this minus 0.28. Does it increase or decrease?
Increase.
Like what value do we get for this?
Minus 0.31.
So we are getting minus 0.31.
311.
So if I plug in, instead of minus 0.28, if I plug in minus 0.31, my E0 cell would become what? Instead of 1.05, it would become, if I add, that's 3, that's 1.03, 1.0, what do you?
1.01.
Then you do this again. This is going to become 1.09.
1.08.
8.
1.08 sir.
1.08. So now he's talking about the E0 cell. So the E0 cell would become more positive. Is that clear?
Yes sir.
So just remember, be careful. He wasn't talking about the cobalt electrode. He was talking about the overall E0 cell. So if you plug in the new value, so it becomes more positive. Clear?
सर जब हम
अगर वो half cell की बात करता
if he was talking about this thing, then it would have become more negative. It is becoming more negative. So just remember, मैं थोड़ा सा confusion दूर कर लूं कि the Nernst equation will only be applied to the half cell, to the electrode. This one or this one, their value will change. It will either increase or it will either decrease. You're going to use that. You can't apply the Nernst equation on the overall equation. You're going to take that value, plug it in this equation over here, and then you'll find out what will happen to the E0 cell. Will it become positive or will it become negative? Okay. Clear?
सर
हाँ जी.
Yes.
सर देखिए, जब हम लोग कोबाल्ट 2 प्लस 2 इलेक्ट्रॉन वाली इक्वेशन की बात करते हैं, जब अगर हम लोग कोबाल्ट 2 प्लस की कंसंट्रेशन कम कर रहे हैं तो इक्विलिब्रियम विल शिफ्ट टुवर्ड्स द लेफ्ट साइड, राइट? तो इसका E0 सेल पे क्या इफेक्ट पड़ता है?
पहले तो ये बताओ इसको क्या होता है? What happens to this? This becomes more negative, right?
मतलब जब इक्विलिब्रियम बैकवर्ड शिफ्ट करेगा so it becomes more negative.
नहीं, but this electrode becomes more negative. Not the overall cell. We're not talking about.
वही.
So the electrode becomes more. The electrode becomes more negative. We even calculated it. That the decreased concentration, we figured out that it becomes minus 0.31. So then we're going to use that value and we're going to plug it in this whole equation, reduction E0 minus oxidation E0, right? And then you're going to find out what happens to it. So the overall E0 cell, higher potential minus the lower potential. Now the lower potential is even lower now. So जब वो difference निकालोगे, it's going to come out to be more positive. Is that clear?
Yes, sir.
बस the main crux is that don't connect the E naught cell directly to the the Nernst equation directly to this equation. You can't do that. Okay? You can only apply it to the electrodes. Once you have these new potentials, whether they're higher or lower, you'll be able to figure out what happens to the E naught cell based on that. Okay. So ये वाला iron 3 ions can oxidize vanadium metal. Construct an equation for the reaction. Now this is, I mean, if you do this question properly, it's going to waste a lot of time, okay? Because it's this is one example of a chain reaction. Vanadium with iron 3 ions, right? Just make sure that for some ions, okay, I'll just go through this again. For some ions, make sure you know that they have a chain reaction, especially vanadium. Vanadium, manganese even. As here's your Fe3 plus equation, right? No, not this one.
So chain reaction में नीचे वाली आएगी ना Fe3+ और 2+ वाली.
Higher potential gains electrons, right? This is the highest potential, it's 0.77. So that's going to gain electrons, right?
Yes, sir.
I said that's 0.77. And you've got vanadium on the other side. Now, vanadium is the lower potential, so it loses electrons, right? Remember, that was 0.77, right? So this is the lower potential. अब ये के, so that is the lower potential. Vanadium loses electrons and it forms vanadium 2+. The vanadium 2+ is still lower potential. So the vanadium 2+ is going to get oxidized further. It's going to again lose electrons and it will form vanadium 3+. The vanadium 3+ compared to 0.77 is still a lower potential. So that means the vanadium 3+ would again lose electrons to form this thing. Uske baad, after that, the reaction will not happen because VO2+ is not a lower potential compared to 0.77. So as long as you have Fe3+, 1 electron, and Fe2+, and this is 0.77 volts, this will continue to gain electrons as long as it is the higher potential. And vanadium would continue to lose electrons as long as it is the lower potential. I said a problem here, even if you do this very quickly, it's still going to take a lot. It's a 2-mark question, but it's still going to take a lot of time because you have to make 3 separate reactions. First one would be Fe3+ reacting with vanadium, right? Is there a way to avoid all those reactions? I'm just thinking, because at the end of the day, we're going to directly jump to this. Probably not. I mean, you would have to
last equations ले लें दोनों की.
नहीं, last नहीं ना, क्योंकि बीच वाला step खा गया ना आप. You have to. नहीं, मतलब end में last में जाना है. What you can do is either make 3 separate reactions. Fe3+ first reacting with vanadium, then Fe3+ reacting with vanadium 2+ and getting it oxidized. Then Fe3+ reacting with V3+ getting it oxidized. Okay? You're going to form 3 reactions and then you're going to add up those 3 reactions. Or what you can do is you sum up all these 3 reactions. If I try to sum this up, what will happen if I add them? Because all 3 reactions are happening, right? So if I add them up and I write just one reaction, so what is happening? The V2+ gets cancelled out, right? Okay, if I add them up, it's going to come on both sides. The V3+ will get cancelled out as well. So what is happening is the vanadium. You can remember this entire thing is going backward, right? So I've got vanadium on my right side. And I've got a water molecule, right? Just one second, this thing is...
Sir, इनके पे E की values भी add होंगी?
नहीं. You remember that they're separate steps, okay?
तो E की value को हम क्या करेंगे?
So there's 3 separate reactions. And remember, there's 3 separate reactions. Fe will react with vanadium. That will have a different potential. Fe3+ will react with vanadium 2+ oxidized, and that's a separate step. Do you know energy profile diagrams? You've got intermediates, then there's another intermediate, then there's another intermediate. So they're actually separate reactions. So you can't.
नहीं सर, मेरा मतलब ये है कि अगर नहीं सर, what I'm asking is कि अगर वो अगले स्टेप हम लोग तो डायरेक्टली कर रहे हैं, अगर वो अगले स्टेप में हमसे वो डिफरेंस पूछे तो फिर हम कौन सी ई की वैल्यू यूज करेंगे?
मैं कह रहा हूँ नहीं कर सकते ना, you can't do that. क्योंकि
अच्छा ठीक है सर.
it's 3-4 separate reactions that are happening, ठीक है? So I'm just trying to make this, because it's just a 2-mark question, but I mean, if you want to go into detail, it's a very long question if you want to do it stepwise. So we're just trying to do this very quickly. Okay, I've just added all 3 reactions. I know all of them are losing electrons. So I've put them in one step, cancelling out everything that's on both sides. In this case, I'm not worrying because I'll do that at the end because they're all losing electrons. So the electrons will add up. I mean, my equation at the end will have electrons. I've got vanadium plus water on the right side. I've got 2 electrons, 1 electron, and that's a total of 4 electrons, right?
Mm-hmm.
Then I've got VO2 plus 2H plus 1. VO2 plus 2H plus 1 on this side. And I know that these are the ones that lose electrons, right? In all cases, these are the lower ones. And then you're going to add them up. The first equation has to be, now you're going to balance equation, balance the electrons. So you're going to multiply the first one by 4. So it's going to be 4 Fe3 plus, that's your reactant. Or this side we've got vanadium as the reactant, and the product is going to be, in the first one, the product is
H को नहीं लिखेंगे हम.
कहाँ पे H? ये वाला?
H2H. Yes.
हाँ, product में आएगा ना. It's getting formed.
अच्छा. H2O को भी नहीं.
हाँ, H2O लिखना था, वो लिखना था. That's your reactant. As I've got VO2 plus and I've got 2H plus 1, right? So that is my final overall equation.
सर मतलब जो आपकी लोअर वाली वैल्यूज होंगी उनकी तीनों इक्वेशंस को सम करना है और जो हायर होगी उसको एज इट इज छोड़ना है. और आखिर में बैलेंस करके बस सम कर देना.
हाँ, तो वही आ रहा है. अब लेकिन इसका प्रॉब्लम है कि it's just a 2-mark question, ठीक है? You can't waste so much time on it because the other way.
ये तो it's coming the other way around. वहाँ पे तो हमारे पास 4 electrons.
कहाँ पे? नहीं, मार्केट स्कीम के साथ कह रहे हो?
जी जी.
मार्केट स्कीम वही है.
नहीं वही है.
हाँ. ठीक है. मैं बस इसको, it's just a 2-mark question. My only problem with this question is that how do you do this very quickly, ठीक है? And remember, this happens for vanadium. This will also happen with tin sometimes. ठीक है? For example, I will do another one. Okay, if you have tin, तो कहाँ पे tin? Tin is over here.
अच्छा सर, the resultant equation it's not reversible.
No, it's not going to be reversible because Fe was the higher potential, so it would be gaining electrons, right?
Okay sir.
And these were lower potentials compared to Fe. Vanadium lost electrons to Fe, then vanadium 2 plus was formed, it lost electrons, so they all lost electrons, right?
सर ठीक है, लेकिन मार्किंग स्कीम में the equation is written backwards.
किस तरह backwards?
VO left side पे नहीं थी.
Fe3 plus V plus H2O वही है.
Okay सही.
ठीक है, मतलब हमारा भी वो V
yes,
plus, ठीक है, it's the same thing. इसका एक और, I'll just try and do some other ones quickly. Okay, you have another reaction similar to this. There are actually just 3 reactions which I know of. Iodine reacting with tin. Iodine is this one. This is 0.54 volts. And tin is over here. Okay, so they're reacting it with tin. Now see, tin has a lower potential compared to iodine, right? So iodine is the one that's going to gain electrons. And tin, which has a lower potential, minus 0.14, is the one that's going to lose electrons. It's going to form tin 2 plus, right? But once that tin 2 plus is formed, it's still a lower potential. So the tin 2 plus is going to lose electrons again. Clear?
Yes.
So what you can do is you can just sum up these equations. So the 2 plus will get cancelled out. So basically it's.
So you took 0.15 per.
0.54 है ना? So it is still the lower potential. It was the lower potential, minus 0.14. Compared to iodine, iodine is the one that's gaining electrons. And tin is the one that's losing electrons. So tin loses electrons, forms tin 2 plus. Once it forms tin 2 plus, it is still the lower potential compared to iodine. So it's going to lose electrons again. Is that clear?
Yes, sir.
फिर 10 2 plus वो cancel हो गए दोनों. 10 2 plus दोनों cancel हो जाएंगे और फिर आपके पास S और tin plus.
And if I sum them all up, it's going to be tin 4 plus 4 electrons, and on the other side it's going to be 10, and all of them are losing electrons. So that one is gaining electrons, this is going backward, right?
Mm.
And the same thing happens with Mn as well. But for Mn, remember this, whenever you have, for Mn, there's a shortcut. The shortcut is whenever you have MnO4 minus 1 acidified, don't use the 1.67, although this is the higher potential, so you should, you'll be tempted to use that equation, but instead वो बीच वाले steps अगर खाने ना बीच में write करने, तो just instead directly use 1.52 volt equation. So for Mn, there's a shortcut which is like if you react anything with Mn, let's say Fe3 plus is reacting with Mn, right? So Fe2 plus is the lower potential, right? So it loses electrons, right? With acidified MnO4 minus 1. So it loses electrons. So what would happen? MnO4 minus 1 would gain electrons, but it's going to be this equation. 1.67, that's the higher potential, right? And it forms MnO2, right? Now, when you look at MnO2 acidified is also still the higher potential. So it would gain electrons again. And it will eventually form Mn2 plus. Then when you look at Mn2 plus is a lower potential. It's no longer the higher potential. So it's not going to gain electrons anymore. So the reaction will stop at this point. Okay, so Fe2 plus being the lower potential would lose electrons, and MnO4 being the higher potential would gain electrons to form MnO2. But then that MnO2 acidified is still the higher potential. So it will again gain electrons. Again, इसका shortcut ये कि start में ना, you don't have to go. The shortcut is just use the 1.52 volt equation. So you'll directly end up with Mn2 plus. Over there you're also ending up with Mn2 plus, but it just involves a lot more steps. This way you'll just directly end up with Mn2 plus. Okay, so just remember this shortcut that for MnO4 minus 1 acidified, just use this 1.52 volt equation. So उसमें फिर बीच में करने की जरूरत ही नहीं है. वरना वो फजूल में ना you'll first make MnO2, then that MnO2 will turn Mn2 plus. End में वही बनाना है, तो just use this equation. ठीक है? Is that clear?
Yes, sir.
Yes.
But again, it was just a 2 mark. It was just a 1 line question. चलिए ठीक है, ये फिर कल कंटिन्यू करते हैं, ठीक है? क्वेश्चन तो नहीं है किसी के?
नहीं सर, thank you.
Nice. Thank you.
ठीक है.
Sir.
Yes.
Is it okay to do zero dilution on paper 5 tomorrow, if you have time?
ठीक है, we'll try paper 5 tomorrow, right?
Yeah, I think zero dilution is the one that is give me a bit of a headache.
Sure. Then somebody, so I will do serial dilution. We'll do the reaction kinetics questions as well tomorrow then.
Okay.
Okay.
All right. Okay.
Sir, this class is being recorded, right?